Think you've grown? Think so?
Some things grow at a steady pace. For example, children add about the same number of inches to their height each year. Plants often grow at a steady rate too, adding a fixed amount in a given time period. When we graph such growth, we get a straight line, so we call this linear growth. But other things grow faster than this. Many animal populations with enough food and no natural enemies tend to multiply themselves by a fixed amount each time period. The result can be a population explosion with dire consequences. It's this kind of rapid growth that we'll study in this unit. We'll see that when growth results from multiplying by a fixed amount in each time period, it is called exponential growth. We'll learn that exponential growth will eventually surpass linear growth no matter how big a head start the linear growth has. We'll see that we can take the logarithm of our data to turn exponential growth into linear growth. And we'll learn about residuals, which are used to tell us how much data points deviate from an overall pattern. Hordes of ugly, hungry creatures invade a town. No, it's not a grade B horror movie. It's real life. These are gypsy moth caterpillars overwhelming a small town in Massachusetts in 1981. In that year, the population of gypsy moths boomed and homeowners despaired. Usually, animals don't have outbreaks like this because their numbers are kept in check by predators, disease, and food shortages. But the gypsy moth has few natural predators and reproduces at a prodigious rate. A single female can lay as many as 1,000 eggs. Let's take a closer look at this reproductive potential. Let's begin with a single pair of moths. If the female lays 1,000 eggs, that means a pair of moths can produce up to 500 new pairs every year. Each of these 500 pairs will, in turn, produce another 500 pairs, which is the same as saying that we multiply 500 by 500 to get the population in the second year. Multiplying again by 500 gives the population in the third year, and so on. This kind of increase, when an amount is multiplied by a fixed number in each time period, is called exponential growth. As we can see, exponential growth is explosive. At the rate our moths are reproducing, there will be about 62 billion pairs in the fourth year. What we've just seen is potential growth. But does the real-life population of gypsy moths actually follow an exponential pattern? Well, we can't go out and count billions of individual moths, but we can estimate their population by counting the number of acres of trees that have been stripped by the ravenous caterpillars. Since we want to see change over time, we put time on the horizontal scale and acres of defoliated trees in millions on the vertical scale. Plotting our data on the graph, we see that the devoured acreage roughly quadrupled each year leading up to an outbreak in 1981. This is an exponential curve. It shows what would happen if the quadrupling were exact. The exponential curve fits the actual data well. But the dashed line is an extrapolation. It's what would happen if the food were unlimited and no other factors came into play. Of course, the real world isn't usually like that. In 1982, the bust came. A viral disease decimated the moth population, much to the relief of homeowners. Still, some moths always survive a bust, and the exponential nature of their reproduction assures that boom and bust cycles will continue indefinitely. The surprising nature of exponential growth, a slow start followed by an explosive increase, is illustrated by an old fable. Once upon a time, a clever courtier, that's someone who hangs around the palace, invented a new game called chess. He made a chessboard and taught the game to the king. The king was so pleased with the new game that he asked the courtier to name his reward. The courtier pondered a moment and then replied, "I'd like 1 grain of rice placed on the first square of the chessboard, 2 on the second, 4 on the third, and in this fashion let the number of grains of rice double for each square of the chessboard. The king quickly agreed. After all, the board had only 64 squares. But as the king's servants began to carry out the order, it quickly became obvious that the king had been too hasty. The courtier had set up a pattern of exponential growth. The number of grains on each square is twice that of the one before it. That meant big trouble for the king. By the 21st square, the servants needed more than 1,000,000 grains of rice. And all the rice in all the kingdoms of the world wouldn't be enough to put on the last square. The story usually ends here, with the courtier gloating at his cleverness. But we can imagine what might have actually happened. After all, kings have a way of winning arguments even when they're up against mathematics. Still, the king did learn a lesson. No matter how slowly it starts, exponential growth can produce staggering results in a surprisingly short time. For example, let's redo our fable with a reward we'd prefer to grains of rice: cash. Suppose we had a choice: $1 billion for each square of the chessboard, or just $1 on the first, but doubling on each successive square as in the fable. For the linear pattern, we start with $1 billion on the first square. For the exponential pattern, just $1. On the second square, we add $1 billion for the linear model and multiply the dollar by 2 for the exponential model. On the third square, add another billion and multiply by 2 again for the exponential. On the 8th square, we've piled up a fortune for the linear model: $8 billion, compared to a measly $128 for the exponential. But the slow start is again deceptive. On the 37th square, the exponential pile, $68 billion, surpasses the amount on the linear pile, $37 billion. And the exponential amount on the 42nd square is greater than the sum of the money on all the squares of the linear model. Let's graph this situation. We'll put the number of squares on the horizontal scale and dollars, in tens of billions of dollars, on the vertical scale. Here we go. Watch as the linear growth begins climbing quickly while the exponential line remains practically flat. After 30 squares, linear growth has piled up $30 billion. Exponential growth, multiplying by 2 on each square, is just above $500 million, which still looks like nothing on this scale. But now the exponential doubling really picks up. By the 37th square, as we just saw, the exponential fortune is $68 billion, surpassing the linear fortune of $37 billion. And the constant multiplying then quickly pushes the exponential fortune to the sky, while the linear fortune continues its plodding additive growth. Even with $1 billion head start, linear growth is eventually left in the dust by exponential growth. Sometimes cases of exponential growth in the real world make intuitive sense, as we saw with the reproduction of animals. But the same kind of exponential patterns can show up in some more surprising settings. This is a graph of annual oil production worldwide. It's easy to see that production has been growing over the years. And it looks like the rise in production could be exponential. But how can we tell? Well, we can use an important mathematical fact. If growth is really exponential, taking the common logarithm of each year's oil production and plotting them against time will result in a straight line. So we can take each production figure from the original graph, find its logarithm on a calculator, and plot that at the corresponding time on a new graph. You end up with exactly the same information, just shown in a different way. It's a lot easier to tell whether the overall pattern of a plot is straight than whether it matches the shape of an exponential curve. So to see if the growth of oil production is exponential, we check whether the plot of the logarithms is linear. Now, we don't expect real data to be exactly exponential. At most, an exponential curve will be a good description of the overall pattern of change. So we don't expect the logarithms of world oil production to fall exactly on a straight line. They don't. But the overall pattern is close to linear. We see that for most of this century, the amount of oil the world used was increasing roughly exponentially. Let's take a closer look at this situation using more data. Again, we've used logarithms to transform the data from an exponential pattern to a roughly linear one. We can see that the overall trend is still linear, but that the data points in recent years fall significantly below the line. The vertical deviation of data points from a fitted line are called residuals. They get their name from the fact that they show what's left over from the overall pattern represented by the line. The size of the residual tells us how far the data point deviates from the fitted line. The larger the residual, the larger the deviation. The residuals allow us to accurately measure the deviation of a data point from the overall pattern. We can see the oil residuals even more clearly if we plot them against time with a reference line at 0. Plotting the residuals like this lets us magnify the deviation, making it easy to spot patterns. The biggest deviations from exponential growth, in other words the largest residuals, are here, in the most recent years. Oil production falls far below the level we might have predicted by extrapolation. But the residuals also show other deviations from the 100-year pattern of exponential growth. There are strings of rising or falling residuals that signal periods of faster or slower growth. Oil production grew more rapidly than the long-term rate between 1900 and 1929. Production increased more slowly during the Great Depression and during World War II. Only after the war did oil production return to an above-average growth rate, which lasted until the mid-70s, when consumption and production began to level off. So an exponential curve describes the big picture of world oil production for about a century. And residuals help us see that this long-term pattern is an average over periods of somewhat slower or somewhat faster growth, which coincide with major events in the history of the 20th century. In this unit, we've looked at exponential growth, which results from multiplying a fixed amount over time. We've seen that although such growth starts out slowly, it increases explosively later on, and will always beat out linear growth in the end. We saw that we can convert an exponential curve to a straight line by taking logarithms. And finally, we saw that residuals measure the deviation of data points from a fitted straight line. This material has been excerpted from the college television course Against All Odds, Inside Statistics, and re-edited for use in high school curricula. Against All Odds is funded by the Annenberg CPB project. Additional funding provided by these companies and foundations. This adaptation is supported by a grant from the National Science Foundation.